right, so let's get into that question 21.31, which is about the malonic ester synthesis. And it just says provide an efficient synthesis for each of these compounds. So what I have in the green box in A, those two carbons, meaning this carbon and this carbon, those are going to come from the diethyl malonate molecule itself. That means that the rest of the compound is going to come from the alkyl halide, right? So what's our alkyl halide going to be? It's going to be a 5-membered ring with a methylene and then some kind of leaving group like that. So it could be a bromide, it could be a chloride, it could be an iodide. That's neither here nor there. So with all that in mind, I'm just going to move that down. And here's what our synthesis is going to look like. We're going to start with diethyl malonate, which we talked about at length in the last video. So there's our diethyl malonate. Step 1 is we treat it with sodium ethoxide. Now, what that does is it generates the doubly stabilized enolate, which can then behave as a nucleophile, and this is going to be our electrophile like that. So I'm going to remove all this, and we're just going to write down for the second step, we're going to write down the structure of our electrophile, which is going to be this compound, and we'll just use a bromide. Again, if you chose a chloride or an iodide, that's totally fine. So what that's going to give you would be this compound. So we have our diethyl malonate, and now at this carbon, what we have is we have our methylene and then our cyclopentyl ring like that. So then in the last step, we treat it with aqueous acid. We hydrolyze both of these to carboxylic acids. We do a decarboxylation. And so in the end, we're going to end up with the final product. So I'm just going to delete all this for now. And we'll write step 3 is, you know what, why don't I do it like this? I'll write out the structure like this. Okay, so I'll put in my 2 ethyl groups. There we go, like that. And then what we'll do is we'll just say after the last step, which is H3O plus, we get the product. So I'll write down your product. Okay, there we go. Okay, so for the next one, you can see that we've got an isobutyl group here that I'm circling in red, and we have an ethyl group over here. So that means we're going to need isobutyl bromide and ethyl bromide. And again, they could be iodides or chloride, it doesn't matter. So let's start out, and first we're going to write down our diethyl malonate. So that's our starting material. So it doesn't matter if we add the isobutyl group first or if we add the ethyl group first. It's neither here nor there. Let's start and we'll add the isobutyl group first. So we'll put sodium ethoxide, and then we'll put isobutyl iodide. Third, we're going to put sodium ethoxide again. Then we're going to put in ethyl iodide like this. And again, it could be bromide, it could be chloride. And what that would give you would be this compound. I'm trying to make sure I get enough space. So I have an ethyl group and I have an isobutyl group. And then you would treat that with aqueous acid and you would end up with the product. All right, so malonic ester synthesis. There you go, malonic ester synthesis. Well, we're going to keep moving in the same vein as the malonic ester synthesis, in that we're going to be looking at alkylation at the alpha position. But now we're going to switch to a different kind of synthesis, and this is called the acetoacetic ester synthesis. So it says it's analogous to the malonate synthesis, the diethyl malonate, using diethyl malonate, the malonic ester synthesis. But now we're going to take our methyl ketone, okay? We're going to take our alkyl halide, and we're going to convert it into a methyl ketone. So we're going to go from Rx to R, and then we're going to have a methyl ketone like this. So we're actually adding 3 carbons. So we're going to add CH2, the carbonyl carbon, and CH3 like that. Except instead of using diethyl malonate, now we use this molecule, which is called ethyl acetoacetate. So ethyl acetoacetate. Okay, so ethyl acetoacetate. and this is what we call the acetoacetic ester synthesis. So we start with ethyl acetoacetate. We do something very similar to the last time. We treat it with sodium methoxide. We generate the doubly stabilized enolate. That can then do an SN2 with a good electrophile like benzyl bromide. And then you blow that apart with acid, and it does a decarboxylation, right? You end up losing carbon dioxide, okay? And when you lose that carbon dioxide, you end up making this methyl ketone. All right, so that's the whole thing, and the mechanism is pretty much the exact same, the decarboxylation. So with all that in mind, let's take a look at an example or two here where we have to use the acetoacetic ester synthesis in order to synthesize these two compounds. So in A, what it means is that these three carbons are going to come from my ethyl acetoacetate. So let's write out the structure of ethyl acetoacetate. It's like you take diethyl malonate, okay, and then what you do is you just erase this, okay, and that's the molecule. That's ethyl acetoacetate. In the first step, I'm going to treat it with sodium methoxide. In the second step, I'm going to treat it with this part, all of these carbons. There are 7 of them in this electrophile, which is going to be this compound. There we go. And again, I could use a bromide or an iodide. And what that's going to give me, and I'll draw the compound that's going to be formed here, would be this, where I have CH2 and I have my cyclohexyl over here. And then all I have to do is treat that with H3O plus, heat it up, and I end up with the product, just like that. All right, for the next one, we see that these 3 carbons are coming from the ethyl acetoacetate. Again, this is called the acetoacetic ester synthesis. And the portion that I'm going to put in a blue box is going to be one of the electrophiles. Maybe I can make a better blue box. There we go. Build back better with a better blue box. Okay, anyhow. And then the other 2 carbons are going to come from another electrophile, which would be ethyl bromide, ethyl iodide, or ethyl chloride. So we'll start out with our ethyl acetoacetate. So let's write out the structure of ethyl acetoacetate. You can add either the benzyl group or the ethyl group first. It doesn't matter. I'll put in the ethyl group first. So first step is going to be sodium methoxide, followed by ethyl iodide. Next step is going to be sodium methoxide again, and then we're going to use benzyl bromide. So that's this guy here. There we go. And you could choose benzyl iodide. It doesn't matter. That's going to give you this intermediate. So you basically start with your ethyl acetoacetate, and you have the ethyl group, and then you have the benzyl group, like that. Then you treat that with aqueous acid, and you heat it up, and you end up with the product, just like that. So there you go. So, what have we covered since our break? We looked at some problems where we actually tried to do a synthesis using the malonic ester synthesis, where we use this as our starting material all the time. This is called diethyl malonate. Okay. And then we basically just, looked at a variation of it, which is called the acetoacetic ester synthesis. And for that, our starting material is always this molecule, ethyl acetoacetate. And again, these types of molecules like diethyl malonate and ethyl acetoacetate, these can be purchased from a chemical supplier. They are not expensive and they are readily available. And so for the diethyl malonate, or the malonic ester synthesis, we ended up making a carboxylic acid. In the acetic ester synthesis, we end up with a methyl ketone. So we make a methyl ketone, right? And you could maybe take that and do a heliform reaction or something. Anyhow, there we go. So that covers all of section 21.5. And with that in mind, let's move on to the last section of new chemistry. There is one kind of new nuance, I guess, in the very last section, 21.7. But this is the last major section of new chemistry, and it deals with what's called conjugate addition reactions. You guys remember the term conjugation because it comes up quite often in organic chemistry. You remember that if we have an aromatic ring, let's say, you know how you have the double and single bonds alternating? Well, we say that they're in conjugation, right? We have double, single, double, single, double, single, right? Conjugation. So a conjugate addition is when if I take, let's say, an alpha beta unsaturated carbonyl, and we saw this earlier on, that we can make an alpha beta unsaturated aldehyde or ketone in an aldol condensation. So this would be called an alpha beta unsaturated aldehyde. We end up with conjugation in the molecule, right? And I explained to you that that is the reason why we do the E1CB reaction, and I explained that because the driving force is that we make that conjugated system. Anyhow, so now that we know what a conjugated system is, and we know that an alpha beta unsaturated aldehyde or ketone is a conjugated system, if you look at the resonance structures of an alpha beta unsaturated carbonyl, which again means aldehyde or ketone, you can see that there are a total of 3 resonance contributors to the resonance hybrid. If you look at this one here, it shows you why the carbonyl carbon is electrophilic. And I know that you would all know that, but if you look at the last one, it shows you why the beta carbon is also electrophilic. And so this is where we kind of introduce the idea of conjugate addition. It means an addition to the beta carbon of an alpha beta unsaturated carbonyl compound. So let's take a look here. It says the beta carbon and the carbonyl carbon are both electrophilic. Yes, we know that. But either carbon can be attacked, but it's going to be dependent on the type of nucleophile that you use. So we have to choose our nucleophile very carefully. And if you're wondering, what are you talking about, Mr. Dion? What I mean is if you have a nucleophile, depending on its identity, it can either do a nucleophilic attack at the beta carbon, or it can do one over here at the carbonyl carbon. And again, that's going to depend on the identity of the nucleophile, and we're going to talk about that in detail now. So if I have a Grignard reagent, right, we all know that Grignard reagents can be thought of, let's say you have an alkyl magnesium bromide. We can think of that as being like a carbanion, can't we? I've told you that many times in this class, right? This would be a powerful nucleophile. Well, when we have a Grignard reagent, the Grignard reagent is going to attack the carbonyl carbon, and we call that 1,2 addition. Why do we call it 1,2 addition? Because what you're doing is you're adding a carbon base group, the alkyl group, to carbon number 1, and we call the oxygen number 2, and you added a hydrogen there in the second step. So that's why we call it 1,2 addition. However, if you use a Gilman reagent, you remember a Gilman reagent, sometimes we call that a cuprate, okay, a cuprate, which is a Gilman reagent. If we use a Gilman reagent, it attacks at the beta position. So we have our alpha position, we have our beta position. Again, if we use the cuprate, it attacks at the beta position, and we call that conjugate addition. Now, if you look at it here, you might think, well, why would you call that 1,4 addition? Because I ended up adding a carbon here, and I added a hydrogen here. That's 1,2, isn't it? But no, it's not, because we actually proceed through an enol intermediate which undergoes a tautomerization. Let me show you what I mean. If you look here, the general mechanism of conjugate addition is as follows. If we number these atoms 1, 2, 3, 4, okay, we have the nucleophile, say our Gilman reagent, for example, attacking the beta carbon. We have the number 4 on there. But what happens is you produce this enolate, which gets protonated in the second step, and then you have an enol which undergoes tautomerization to give you the aldehyde or ketone. So now you can clearly see if we have this numbering that you've added something at carbon number 4, and you've added something at the oxygen which is labeled number 1. So that's why we call it 1,4 addition. Okay, so the key is that it undergoes a tautomerization. All right, so 1,4 or conjugate addition. Now remember, I told you we're going to talk a lot about the identity of the nucleophile. So a stronger nucleophile tends towards 1,2 addition, attacking the carbonyl carbon, whereas less reactive nucleophiles, and if you're wondering, how do I know if it's less reactive? We're going to talk about that. If you have a less reactive nucleophile, it tends to do conjugate addition or 1,4 addition. All right. So if we have a typical enolate, in that case, we're normally going to get a mixture of 1,2 and 1,4 addition. I'll tell you right now, in Chemistry 3111, we try to avoid mixtures when we can, okay? Nobody wants to get a mixture in organic chemistry. They can be pretty frustrating. But if you have a stabilized enolate, right, if you were to take this compound here, So this is called 1,3-cyclohexane-dione. If I was to treat that with potassium hydroxide, I'd end up with this doubly stabilized enolate, right? I have delocalization of the negative charge up here, and I have delocalization of the negative charge over here. So that means it's not as reactive as a regular enolate. And so what it says here is that a stabilized enolate, okay, is going to give 1,4 addition exclusively. So the nucleophilic attack that occurs is going to occur at the beta carbon like this, okay, like that. So when we do this 1,4 addition reaction, we call that a Michael addition reaction. So you would end up, after this step here, after this nucleophilic attack that I've drawn here, what's the intermediate that you would get? I'll draw it kind of carefully down here because I don't have a ton of space, but it's going to look like this, okay, like that. And we're going to have the negative charge up on the oxygen like this. Then what happens in the third step is you treat it with aqueous acid, and that's going to protonate up here, but then you end up with this enol, which is going to tautomerize to give you the aldehyde in this case. Okay, so this is tautomerization after the third step. So that's what we call a Michael reaction, or sometimes I'll call it a Michael addition. So the 1,4 conjugate addition is called a Michael reaction. Again, sometimes I call it a Michael addition. That's what I grew up with. And the nucleophile, we call that the Michael donor. And the electrophile, which is our alpha beta unsaturated carbonyl, whether it's an aldehyde or a ketone, we call that our Michael acceptor. So a Michael donor and a Michael acceptor. Well, with all that in mind, let's take a look at this table here, which covers some common Michael donors and Michael acceptors that we are going to run into in this class. If you're the kind of person who might be interested in writing a standardized exam in organic chemistry or that involves organic chemistry, these are the types of Michael donors and Michael acceptors that you would need to know. So the first thing that I notice about the Michael donors is that if you look at this one, this one, this one, this one, and even this one, is that with all of these, I can easily draw another resonance contributor. Except for the nitro, I can only draw one. But for all the other ones, I can draw two other resonance contributors, right? So I see the delocalization of that negative charge, and also a Gilman reagent is also a Michael donor. So this one here is the cuprate, which is a Gilman reagent. Anyhow, now in terms of Michael acceptors, an alpha beta unsaturated aldehyde or an alpha beta unsaturated ketone, an alpha beta unsaturated ester, which we've made, an alpha beta unsaturated amide, an alpha beta unsaturated nitrile, and an alpha beta unsaturated nitro. These all make good Michael acceptors. So we have our Michael donors and our Michael acceptors. I'm going to add one more to the list of Michael donors, and it's going to come up more later on. But you guys remember an enamine? Remember we talked about enamines quite a bit a while ago? Let's say you have something like this, okay? I'll just put, squiggle bond here, okay? This is called an enamine. And again, we looked at these in chapter 20. But an enamine also makes a good Michael donor because it can do this kind of nucleophilic attack like this, where you can use the pi bond like that as a nucleophile. So I'm going to throw the enamine, and I'm going to show you how we use enamines as Michael donors later on. Well, with all that in mind, let's take a look at a problem here. It says predict the major product for the following of the three following steps and show a mechanism for its formation. So in the first step, we're treating it with sodium hydroxide. That is a pretty simple mechanism, and I don't even like to use the word simple in organic chemistry together, but this is one case where I think it applies. We end up with our doubly stabilized enolate. So I'm going to draw that out. And when we have a doubly stabilized enolate like this, this makes a good Michael donor. So this is our Michael donor. And we have an alpha beta unsaturated ketone, and so that is going to be a Michael acceptor. Let's draw the structure of the Michael acceptor. It's going to look like this. Right, there we go. So this is our nucleophile. This is the electrophilic center, right, the beta carbon. So what do we have? We have nucleophilic attack over here. We move this pi bond up here. And let's draw what that's going to look like. So we end up with something that looks like this. We have these 5 carbons in a row like that. And then we have 1, 2, 3 carbons. So let's draw those 1, 2, 3 carbons. On the 3rd carbon, I'm going to have a carbonyl. And I'm also going to have, sorry, it's not a carbonyl, is it? I'm going to have to erase one of those bonds. There we go. I'm going to have this enolate like that. So then in the next step, we're going to treat it with aqueous acid. That's going to do a proton transfer like this. We end up with the enol. Okay, so let's draw the enol form. This looks like this. There we go. There we go, like that. And then that is going to undergo a tautomerization. I'm not going to draw the mechanism of tautomerization in the interest of time. And we're going to end up with this compound. So we have this carbonyl here. There we go. And we have our cyclohexyl like that. And there you go. There's our Michael addition. So one thing I noticed about Michael addition is you usually have, 1, 2, 3, 4, 5. So whenever you have like 1, 5 functional groups, this usually means you're dealing with some kind of Michael addition reaction. It's kind of a thing that you look for when you're an organic chemist. Let's try another problem. It says here, using diethyl malonate as your starting material, any other reagents of your choice, show how you would prepare the following compound, since there's only one of them here. Well, let's see, what would we want to do here? If this is the product of a diethyl malonate or a malonic ester synthesis, from the malonic ester synthesis, we would get these carbons right here. Let me use my green pen, okay? So we would want to use, we'd get these carbons, right? We'd get this carbon and this carbon from the diethyl malonate. So that means that all of this portion, oh, I get it now, okay? So all of this portion here is going to come from our electrophile, right? So how are we going to put all this together? Right? We've got to put all this together somehow. Well, what I think we should do is we should do a retrosynthesis where we're going to have our diethyl malonate, okay, like this. I'm trying to think of the easiest way to explain this. And I know that the 2 carbons that I have in green, let's say they're going to come from this carbon and this carbon. So where is all the rest going to come from, right? It's going to come from something that's going to look like this. I've got the carbonyl. Oops, I'll use my black pen again. I've got the carbonyl like this, okay? I've got another, and then I've got 2 methyl groups on here like this. So that means that this could be a Michael acceptor, right? So because from this compound, I can make a Michael donor, can't I? Right? If I take diethyl malonate, so let me show you what I mean. I'll take diethyl malonate, and if I treat this with sodium methoxide, what do I end up with? I end up with the doubly stabilized enolate. I'm just trying to do a shortcut here, so copy and paste it over here. There we go. So I have my negative charge here, but remember, this is a Michael donor, right? And I need to add all of these carbons here, and this piece would make a good Michael acceptor. So now all I have to do is draw a reaction arrow right here, and I'll even draw the mechanism or part of it. So now that I have this, okay, I'm going to do my nucleophilic attack. Son of a gun, where's my red pen? There we go. My nucleophilic attack, like this, which is going to give me this intermediate. draw that. Okay. So there's this piece, and then I have 1, 2, 3 carbons like this, and on this guy I've got these 2 methyl groups like that. But again, I made the same mistake that I did on the last one, where I'm not going to have the ketone. I'm actually going to make an enol, aren't I? Right? So I'm going to delete one of those bonds. I would start with the enolate, right? But then I'm going to treat that with acid, which is going to protonate it. Okay, so I'm going to heat that up. Not only is it going to protonate this to make the enol, which will undergo tautomerization, but it's also going to hydrolyze both of these so that I end up with just the carboxyl here and the methylene, right, which is going to come from here. So if you're not 100% sure, look, I'll show you what I mean. So you're going to take it and you're going to end up protonating and undergoing tautomerization. Okay, and I'm kind of drawing it in too many steps here, but you're going to end up with this. Okay, and then once you keep heating this in acid, it's going to decarboxylate, right? You're going to lose all this, and you're going to lose that to have a carboxyl group, and that's your final compound. You end up with the product like that. All right, give me a thumbs up if you follow me on that one. So this is like a malonic ester synthesis. But now we're using the diethylmalonate as a Michael donor. So if we go back here, but if you look at your list of Michael donors, you can see that diethylmalonate can be a Michael donor. And then what did we use? We used an alpha beta unsaturated. Unsaturated ketone to be our Michael acceptor. Does that make sense to everybody? All right, cool. Thanks, Gilbert. Thanks, Skylar. Good. All right. So conjugate addition. Only a couple more reactions here. We have the stork, what's called the stork enamine synthesis, and one more that's called a Robinson annulation. But the good news is that if you understood what I've been talking about thus far, if you're like, oh yeah, I can connect all these dots together, well then it won't be that much of a stretch for you to figure out what's going on in the stork enamine synthesis. So let me just get ahead here and try to find what I'm looking for. Just give me a second, which is this here. So you remember I told you that if you take just a regular ketone or aldehyde that has an alpha proton and you make an enolate, I told you that doesn't make a good Michael donor. Okay, it makes a very poor Michael donor because it's too powerful of a nucleophile. It'll usually do 1-2 addition or a mixture, so it's kind of useless, really. But there is a way to use just a ketone or aldehyde and do a Michael addition. And it was developed by a chemist at Columbia University. His name's Gilbert Stork, and this is called the stork enamine synthesis. Now, I know that everybody who's hearing the sound of my voice is in this class, and just last week or something, we looked at chapter 19, and we talked about how to make an enamine. Right, so what you're going to do is you're going to take your ketone or aldehyde, you treat it with a secondary amine, so that's very important. It's going to be a secondary. If it was a primary amine, then you end up with an imine, right? But with a secondary amine, catalytic amount of acid, loss of water, you make an enamine. Enamine. And the thing about an enamine is that it's also a Michael donor, okay? And the reason why is because if you draw this lone pair here, it's a good nucleophile, but it's not nearly as powerful an electrophile, or it's not nearly as powerful a nucleophile as an enolate like that. This is going to give you 1, 2, and 1, 4. Once you form the enamine, it's only going to give you 1, 4 addition. Okay? So it says here the enamines behave like an enolate. They're nucleophiles. However, when you look at the enolate ion, you only have a negative charge in the molecule, whereas in the enamine, you can draw a resonance contributor where there's a negative charge on this carbon here, but there's also a positive charge here, right? So the charge over here is -1 and the charge here is 0. So an enamine is nucleophilic but less nucleophilic, and therefore it makes a Tsatsi Michael donor. Kind of an interesting way to make a Michael donor, and the nucleophilic attack would look exactly like what you think it would, right? You can draw it the way that I drew, whereas I like to draw the arrows from the enamine. If you want to draw this resonance contributor and draw the nucleophilic attack like that, there's no problem. But check it out. after your nucleophilic attack on your Michael acceptor, look what you end up with. You end up with an iminium and an enolate. So overall, your charge is still 0. There's no charge at all. And then when you treat the whole thing with aqueous acid, here you make an enol, which undergoes tautomerization to give you a ketone. And in section 19.7, we saw how an iminium, when you treat it with aqueous acid, it blows it apart to give you a ketone. So you literally just blow the whole thing apart, and you end up taking both of these and you convert them both to ketones like that. So again, you see how they are 1, 2, 3, 4, 5 substituted, my 2 functional groups. Whenever I see 1,5 substitution of functional groups, I usually start thinking about some kind of Michael addition. Okay. So overall, the stork enamine synthesis, very important synthesis in organic chemistry, is a 3-step process. Step 1, you take your aldehyde or ketone, treat it with secondary amine. I mean, here it just says R2NH. I like to use dimethylamine, so R2NH could be many different things. I like to use dimethylamine, okay, either way. Then a catalytic amount of acid, water, you make the enamine, you may have a Michael donor, then you have a Michael acceptor, like your alpha beta unsaturated ketone that's here. You form an iminium and an enolate, you treat it with aqueous acid, and you end up with a 1,5-dicarbonyl compound. Kind of cool, huh? So I'll write that down here. This is called a 1,5-dicarbonyl. There we go, a 1,5-dicarbonyl. So stork enamine synthesis, a 3-step process. It says using a stork enamine synthesis, show how you might accomplish each of the following transformations. So here's what I do, okay? We're given a ketone, okay? We're going to have to take that ketone and convert it into an enamine, aren't we? Right? Because if we were to try to make an enolate on this, that's going to do a mixture of 1,2 and 1,4 addition. It's not super useful. So here's what we're going to do. If this is our alpha carbon here, so we have our alpha and our beta carbon here off of this carbonyl, what we're going to do is we're going to break that bond for our retrosynthesis. And it probably just deleted everything I wrote down, but no, it didn't. Okay. So for our retrosynthesis, we're going to have, what is our enamine? Right? We're going to have our enamine look like this. Okay, like that. And if you want to put 2 R groups there, that's okay. I'll just leave them as 2 methyl groups. So that's the enamine. That's going to come from our ketone. And what's our Michael acceptor going to look like? It's going to have all of this piece right here, but you're going to have a double bond here. Okay, so let's write that down. So we have our Michael acceptor, which is going to be this guy right there. So those are the 2 compounds that we need. Now, overall, what's the synthesis going to look like? Step 1 is going to be to treat the compound with dimethylamine or a dialkylamine, a catalytic amount of acid, loss of water. The second step is going to be to treat it with our Michael acceptor, which is going to be this alpha beta unsaturated ketone. And then in the third step, we're just going to treat it with aqueous acid, and that's going to blow everything apart to make our 1,5-dicarbonyl, right? Look, 1, 2, 3, 4, 5. So we end up with our 1,5-dicarbonyl. Let's try it again. We have a ketone. That's going to make a miserable Michael donor because it's going to give us a mixture. So the first thing we're going to have to do is convert that into an enamine. Let's do that first. I'll use dimethylamine, a catalytic amount of acid. We're going to lose water, and we would end up with this molecule. So now we have an enamine that looks like this. Okay? Now, these 5 carbons are these 5 carbons here, right? So this is our alpha carbon here, and then this is the new bond that was made, is this bond here. Okay? So what does that mean? In terms of our retrosynthesis, our Michael acceptor is going to be this alpha beta unsaturated carbonyl compound. So now I'm going to take my enamine and I'm going to treat it with that Michael acceptor. It's just an alpha beta unsaturated ketone. You can even practice drawing the curved arrows if you want. So you're going to get 1,4 addition like this. I'm not going to draw the intermediate. I suppose I could, but your intermediate is going to look like this. So, oops, let me get my black pen out. It's going to look like this. So we're going to have the double bond to the nitrogen. It's going to have a positive charge. That's our iminium. We're going to have our 6-membered ring. We're going to have the negative charge over here. So again, this is our iminium ion. This is our enolate ion over here. And then what we do in the last step is we treat it with aqueous acid. It's going to hydrolyze the iminium. It's going to protonate this to make an enol, which is going to tautomerize to give us the ketone. And that is going to give us our product. And there you go, a couple of stork enamine syntheses. The last new reaction really in this section or in this chapter, and there's one more nuance like I told you in section 21.7. It's called the Robinson annulation reaction. Annulation, there's might be a little bit of history of the word annulation in the textbook, but annulation just really means formation of a ring. Okay, I don't know, enough Latin, but I know that in French, annul means ring. So the word annul is like if you have a ring on your finger, for example. So annulation is the formation of a ring. Anyhow, so Robinson annulation is really nothing more than a two-step process that is a Michael addition followed by an intermolecular aldol condensation. And it's a really common way of making rings in organic chemistry. It's not uncommon at all. Now, the way that they've written it out here, I always thought it was kind of interesting, is that they show you the whole thing, right? If you were to take this, treat it with sodium hydroxide, you end up with a good Michael, right? You end up with a good Michael donor because you have a doubly stabilized enolate. You have a Michael acceptor over here. Michael acceptor. Okay, and you could even practice drawing the mechanism of 1,4 addition. You form the enolate that undergoes tautomerization to give you the ketone. Then if you're treating this with sodium hydroxide, what's that going to do? It's going to form this enolate, which can then do, an intramolecular aldol condensation. And I'm not going to draw the mechanism for that either. But again, you see that it's just a Michael addition followed by an intermolecular aldol condensation. We end up with an alpha beta unsaturated carbonyl, and we end up forming a ring in the process. Now, what I want to point out to you guys is that going from the starting materials to the final product, you see that it's just sodium hydroxide, right? So there's no other reagents. And so all of this can be done in one flask or one vessel. Okay, it's just one reaction, sodium hydroxide and heat. That's all it is. And you can start from the Michael donor, the Michael acceptor, and you end up with the bicyclic compound. You don't have to isolate this whatsoever. It's just showing you the intermediate so that you understand, where it comes from. Well, let's take a look at a question that involves a Robinson annulation. It says identify the reagents that could be used to prepare the following compound via Robinson annulation. Not simple when you look at it the first time. And so what I want to do is go back to this question here and or this example rather, and kind of dissect it, right? Because if you look at the alpha beta unsaturated carbonyl, right, if you break that, then you could get back to this part right here. And then you could do a second retrosynthesis, right? Because you have your carbonyl, you have 1, 2, 3, and then after the third carbon, you break this bond. So that might be a good way to do the retrosynthesis. So if we go here and we break this bond like that, what would that give us, right? What would our precursor look like? Now, if you break that bond, okay, and you make a carbonyl off of here, right, so that you have another aldehyde here, what is that going to look like? Let me show you. It's going to look like this. You've got the carbonyl here, you've got this, and then you've got another carbonyl here. Then you've got this methyl group. Then you've got 1, 2, 3, 4 carbons. So I'll write those here. 1, 2, 3, 4, and on the third carbon, you've got a carbonyl like that. So that's the first precursor. Then, again, going back here, okay, going from the bond that was broken, right? You go off of this carbonyl, you go back 1, 2 carbons, and that's where you break the last bond. So you go back here, here's the carbonyl, you go back 1, 2. So you would break, son of a gun, you would break this bond right here, okay? And then you end up with what? You have the precursor to your Michael donor, which would be this. And then your Michael acceptor would be this guy right here, okay? So those are the two starting materials that you need to do the Robinson annulation. So you literally just start with this compound, this dialdehyde, and we can draw it the same way it's drawn here. So we start out with the dialdehyde. We treat it with the Michael acceptor. We put it in sodium hydroxide. We cook it up, and that's going to give us the final product like that. So again, I think it's best to do this by a two, kind of like a double retrosynthesis, okay? Because the first part is the Michael addition. So this is the retrosynthesis of the Michael addition, and then this is the retrosynthesis for the aldol condensation. Okay, condensation, like that. There you go. Well, that covers all of the new reactions. Again, I told you there's one nuance I want to show you in section 21.7, which is a really good one. You know how a lot of times in this class and in Organic Chemistry 1, when we get to the parts of chapters that dealt with synthesis strategies, sometimes I went through them kind of quickly. I just rushed through them and then say, let's get into the good stuff, the practice. But this one is actually pretty useful because there's so many different carbon-carbon bond forming reactions that we looked at in this chapter. And they yield products that contain two functional groups, like a carbonyl and an alkene, or a carbonyl and an alcohol, or two ketones, right? These are things, that you kind of got to, keep a close eye on. And so some of the main reactions that we learn in this chapter are things like aldol reactions, like aldol additions and aldol condensations, Claisen condensations, that's where we make a beta keto ester, and then the stork enamine synthesis, which is a type of Michael reaction. So Michael reactions or 1,4 additions, right? These are all important reactions that we've learned. So positions of functional groups in a target compound are going to be really helpful. In fact, you've heard me mention this a few times. If I have a 1,5 compound, for example, I start thinking about Michael addition. Well, here are some strategies that Dr. Klein has come up with. If you have a 1,5 compound, whether it's a 1,5 dicarbonyl, you could reduce that to a 1,5 diol, right? So whenever I have a 1,5 functional group in a compound, I'm usually thinking Michael addition, right? So here, if you have a 1,5 dicarbonyl, you'd want to think about the stork enamine synthesis. If you have a 1,3 difunctional compound, whether it's a beta keto ester or a beta hydroxyaldehyde or ketone, then you want to think about a Claisen, like this, Claisen condensation, or an aldol reaction, an aldol addition, something like that. All right. So this is the one variation on a reaction that is kind of new in section 21.7. It's the only thing that isn't really covered in the other section. So hold on to your hats and check this out. It says, we've learned a couple of methods of alkylation. The alpha position of an enolate, we saw that can attack an alkyl halide, right? We said if we have an alkyl halide and an enolate like this, right? If you have this, it can do, attack like that. And we looked at kinetic and thermodynamic enolates. Okay, so that's nothing new. That's point number one. But we also saw that a Michael donor can attack the beta position of a Michael acceptor. So check this out. If you take this alpha beta unsaturated ketone and you treat it with a Gilman reagent first, this is kind of what's happening. It's like you're taking an ethyl anion, okay? And it's like you're doing this. You're doing your nucleophilic attack at the beta carbon, okay? And then you end up with this intermediate. So let me draw the intermediate that's formed. You end up with an enolate, right? Where you have your ethyl group over here. Well, instead of just treating this with aqueous acid, right, to protonate and tautomerize to give you the ketone, if you treat this with methyl iodide, what that's going to do, let me draw the methyl group. So if you treat that with methyl iodide, what it does is this, is you do the nucleophilic attack like this, okay, and then you end up adding two groups or two alkyl groups to what was originally a Michael acceptor, which is pretty cool, huh? So this is kind of new. It's like I'll call it quotations new, right? Because these are two reactions that we looked at before, but I never talked about using this intermediate as a reagent to do an alkylation at the alpha position after the addition of a Gilman reagent, all right, or just a Michael donor. All right, so the review of reactions I think is really helpful. In this one here, we talked about alpha halogenation of a ketone using aqueous acid, catalytic amount, and bromine, and we saw that you could take that and treat it with pyridine to make an alpha beta unsaturated carbonyl. We talked about the HVZ reaction, the Hell-Volhard-Zielinski reaction. You take a carboxylic acid, treat it with bromine, phosphorus tribromide, followed by water, and you end up with an alpha bromocarboxylic acid, just like you did in the first one. The haliform reaction, hey, one of my favorites, right? You treat the methyl ketone with excess sodium hydroxide and bromine, and you actually end up with this compound where you have your carbon and then you have 3 bromine, so that makes it a good leaving group, and then you hydrolyze it. So this is the first step, this is the second step, to a carboxylic acid, so haliform reaction. For aldol reactions, remember we learned an aldol addition, which is no heat in sodium hydroxide. That gives you a beta hydroxyaldehyde or a beta hydroxy ketone. Then we talked about aldol condensation. So that's where we make an alpha beta unsaturated aldehyde. Then we talked about crossed aldol condensation, and we talked about some strategies there. So yeah, we talked about directed aldol reactions. We talked about an intramolecular aldol condensation. What else? We talked about Claisen reactions, crossed Claisen reactions, Dieckmann cyclization, which is just an intramolecular Claisen reaction. We talked about alkylation. So we talked about making a thermodynamic or a kinetic enolate. Talked about that in detail. We did the malonic ester synthesis and the acetoacetic ester synthesis. After that, we looked at Michael additions. So having a stabilized carbon nucleophile like a 1,3-dicarbonyl or a Gilman reagent, for example. We talked about what a Michael acceptor is. We talked about the stork enamine synthesis and why you can't do a Michael addition with just a straight ahead carbonyl compound. You've got to make an enamine first. Then we talked about the Robinson annulation, which is just a Michael addition followed by an intramolecular aldol condensation reaction. And that's it. That's all the chemistry that we looked at in this chapter.